Welcome to Tech with Kaushik. This is set 4 of our DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link in the description. Let us begin set 4. Question number 58. Let's go. The topic for this question is automated recovery. A critical application relies on an Amazon Aurora MySQL database cluster in the US East 1 region, with a cross-region read replica established in US West 2 for disaster recovery purposes. If the primary cluster in US East 1 fails, the operations team wants the read replica to be automatically promoted to a primary standalone cluster. The application must quickly reconnect to the newly promoted primary without requiring manual code changes or redeployments. Which solution will accomplish this automated failover? Option A. Store the current Aurora database endpoint URL in AWS Systems Manager parameter store and configure the application to fetch it on connection failure. Create an Amazon Event Bridge rule that detects an RDS database cluster failure event. Route the event to an AWS Lambda function that promotes the cross-region read replica and updates the parameter store value with the new endpoint. Option B. Configure a latency-based Amazon Route 53 name with health checks pointing to both the primary and replica endpoints. Subscribe an Amazon SNS topic to Amazon RDS failure notifications from AWS CloudTrail and use that topic to invoke an AWS Lambda function that promotes the replica. Option C. Create an Aurora custom endpoint that includes both the primary and the cross-region replica. Configure the application to use this endpoint. Use AWS CloudTrail to detect failure and trigger an AWS Lambda function to modify the custom endpoint's priority. Option D. Create an AWS Lambda function to modify the application's AWS Cloud Formation template to update the database connection string. Create an Amazon CloudWatch alarm monitoring database connections to invoke this Lambda function when connections drop to 0. The best choice is option A. Store the current Aurora database endpoint URL in AWS Systems Manager parameter store and configure the application to fetch it on connection failure. Create an Amazon Event Bridge rule that detects an RDS database cluster failure event. Route the event to an AWS Lambda function that promotes the cross-region read replica and updates the parameter store value with the new endpoint. This works because automating a cross-region database failover requires orchestrating the infrastructure promotion and updating the application's connection context. Amazon RDS emits detailed state changes, like failover or crash events, directly to Amazon Event Bridge. An Event Bridge rule can capture this and trigger an AWS Lambda function. The Lambda function issues the API call to promote the Aurora Red replica to a standalone cluster. The Lambda function then updates the connection string stored in AWS Systems Manager parameter store. Because the application fetches its endpoint from parameter store upon connection failure, it seamlessly reconnects to the newly promoted primary without requiring redeployment. The remaining options can be eliminated because B. Route 53 latency-based routing with names is unreliable for databases because DNS caching, TTL, at the client or OS level can cause applications to connect to the dead database long after failover occurs. Parameter store provides immediate deterministic updates. C. Aurora custom endpoints are regional constructs. A single custom endpoint cannot span across different AWS regions to include a cross-region read replica. D. Modifying a cloud formation template and updating the stack via Lambda is an extremely slow process. A stack update can take several minutes, significantly increasing the application's downtime, RTO, during a critical failover compared to simply updating a parameter store string. The main takeaway is to automate cross-region Aurora failovers gracefully, use Event Bridge to detect the failure, trigger Lambda to promote the replica, and have Lambda update an SSM parameter store or secrets manager string so the application can dynamically fetch the new endpoint. Question number 59. Scenario. A security team maintains an AWS Lambda function in a central management account within AWS organizations. This Lambda function must periodically scan the configurations of all Amazon EC2 security groups across 50 member accounts to ensure compliance with corporate firewall rules. The Lambda function will programmatically retrieve this information by assuming IAM roles located in each of the 50 member accounts. Which combination of IAM configurations is required to allow the Lambda function to retrieve this information successfully? Choose 3. Identify all valid responses. Options. Option A. In the central management account, grant the Lambda function's IAM execution role the permission to perform the STS. Assume role action against the target IAM roles in the member accounts. Option B. In each member account, create an IAM role and attach the AWS managed Amazon EC2 read-only access policy to it. Option C. In each member account, configure the trust policy of the newly created IAM role to allow the STS. Assume role action from the central management account's Lambda execution role, ARN. Option D. In the central management account, attach the Amazon EC2 read-only access managed policy directly to the Lambda function's IAM execution role to authorize cross-account EC2 queries. Option E. In each member account, create a trust policy that allows the member account root user to assume the IAM role of the Lambda function in the central management account. Option F. In the central management account, create an IAM resource-based policy on the Lambda function that grants EC2. Describe security groups access to all member accounts in the organization. You should choose option A. In the central management account, grant the Lambda function's IAM execution role the permission to perform the STS. Assume role action against the target IAM roles in the member accounts. Option B. In each member account, create an IAM role and attach the AWS managed Amazon EC2 read-only access policy to it. And option C. In each member account, configure the trust policy of the newly created IAM role to allow the STS. Assume role action from the central management account's Lambda execution role, ARN. A central AWS Lambda function pulling data from multiple member accounts requires a cross-account IAM architecture. The target member accounts must define the permissions the Lambda function is allowed to exercise. This is done by creating an IAM role in each member account with the Amazon EC2 read-only access policy. B. The member account roles must explicitly trust the central Lambda execution role. This is established by updating the trust policy on the member account roles to allow STS. Assume role originating from the central Lambda roles, ARNC. The central management account must authorize its Lambda function to make the leap. This is done by attaching a policy to the Lambda execution role, allowing it to perform STS. Assume role targeting the member account roles, A. Here's why the alternatives are not suitable. D. Attaching Amazon EC2 read-only access directly to the Lambda function's execution role only grants it permission to read EC2 instances in the central management account, not in the member accounts. E. Allowing the member account root user to assume the Lambda's role in the central account represents the exact opposite flow of access required. F. Resource-based policies dictate who can invoke the Lambda function, not what AWS resources the Lambda function is permitted to access across accounts. Here's a useful exam tip. Programmatic cross-account access for AWS Lambda requires an execution role in the source account with STS. Assume role permissions and a role in the target account with the required permissions and a trust policy pointing back to the Lambda execution role. Next, question number 60. The focus now shifts to high availability. A web architecture deployed in a single Amazon VPC uses a single Amazon EC2 NAT instance located in a public subnet. This NAT instance provides outbound internet access for backend web servers located in private subnets, allowing them to download software updates and access third-party APIs. The architecture currently represents a single point of failure. A DevOps engineer must upgrade this architecture to be highly available across multiple availability zones with minimal administrative overhead. Which combination of actions should the engineer take to achieve high availability for the web tier and outbound internet access? Choose 2. Choose every option that satisfies the requirement. Choices. Option A. Provision additional Amazon EC2 web server instances in private subnets across multiple availability zones and place them behind an application load balancer. Option B. Provision a managed AWS NAT gateway in a public subnet within each availability zone. Update the route tables associated with the private subnets to point 0.0.0 to 0/0 to the NAT gateway in their corresponding availability zone. Option C. Add the existing Amazon EC2 NAT instance to an auto-scaling group that spans multiple availability zones and update the route tables to point to the auto-scaling group ARN. Option D. Provision a single managed AWS NAT gateway spanning multiple availability zones. Update the main route table to point 0.0.0.0/0 to the single NAT gateway. E. Configure an application load balancer in front of the existing single Amazon EC2 web server instance and configure Amazon CloudWatch alarms to recover the instance upon host failure. The correct answers are Option A. Provision additional Amazon EC2 web server instances in private subnets across multiple availability zones and place them behind an application load balancer, and Option B. Provision a managed AWS NAT gateway in a public subnet within each availability zone. Update the route tables associated with the private subnets to point 0.0.0.0/0 to the NAT gateway in their corresponding availability zone. Let's look at the reasoning. To eliminate single points of failure in the architecture, the web tier must be scaled horizontally. Provisioning additional EC2 web server instances across multiple availability zones and placing them behind an application load balancer ensures that if one availability zone or instance fails, traffic is routed to healthy instances. A. The outbound routing tier must also be highly available. EC2 NAT instances are legacy single points of failure. Managed AWS NAT gateways are highly available natively within a single availability zone. By deploying one NAT gateway in each availability zone and updating the route tables for the private subnets to use their local NAT gateway, you achieve high availability and isolation against single availability zone failures. B. The other choices do not work because C. Adding a NAT instance to an auto-scaling group does not provide true high availability. If the instance fails, there is a delay while the ASG provisions a new one. Furthermore, updating route tables dynamically to point to new ENIs requires complex custom scripting. Managed NAT gateways handle this natively. D. Provisioning a single managed NAT gateway provides high availability within one availability zone, but it remains a single point of failure if that specific availability zone goes down. Best practice dictates a NAT gateway per availability zone. E. Adding an ALB to a single EC2 instance and relying on CloudWatch to recover the instance introduces significant downtime, RTO, during the recovery process. High availability requires active-active redundancy across availability zones. Exam tip. EC2 NAT instances are deprecated. To achieve high availability for outbound private subnet traffic, provision a managed AWS NAT gateway in the public subnet of each availability zone and route traffic locally. Question number 61. Scenario. A DevOps engineer manages an AWS code pipeline deployment pipeline that builds, tests, and deploys a microservice. The pipeline includes a manual approval stage before the final production deployment. The operations team requires that whenever the pipeline state changes, especially when a manual approval is requested, a near real-time notification with event details must be posted to a dedicated channel in their custom enterprise chat application using a webhook URL. Which solution will meet these notification requirements with the least operational overhead? Option A. Create an Amazon Event Bridge rule that filters for code pipeline execution state change and code pipeline action execution state change events. Configure the rule to target an Amazon SNS topic. Subscribe an AWS Lambda function to the SNS topic to format and post the payload to the chat webhook URL. Option B. Configure an AWS CloudTrail trail to log code pipeline API calls. Create an Amazon CloudWatch log subscription filter matching the put approval result action. Trigger an AWS Lambda function from the subscription to send the notification to the chat webhook URL. Option C. Add an AWS code build action immediately before the manual approval stage in the pipeline. Configure the buildspec.yml to execute a shell script that sends the pipeline metadata via curl to the chat webhook URL. Option D. Modify the code pipeline settings to natively specify the custom chat webhook URL in the pipeline's notification properties. Configure the pipeline to emit events for pipeline execution state changes. Go with Option A. Create an Amazon Event Bridge rule that filters for code pipeline execution state change and code pipeline action execution state change events. Configure the rule to target an Amazon SNS topic. Subscribe an AWS Lambda function to the SNS topic to format, and post the payload to the chat webhook URL. The main reason is Code Pipeline emits pipeline and action execution state change events to Amazon EventBridge, including approval action state changes. Among the listed choices, A is the only solution that captures the required state changes in near real time and can deliver a custom formatted payload to an arbitrary enterprise webhook. SNS provides fanout and Lambda performs any required payload transformation and HTTP post. Let's quickly check the incorrect choices. B. CloudTrail API call logging is not the correct source for the complete set of code pipeline execution and approval state transitions required by the scenario. C. A code build action can emit a webhook only when that build runs. It does not represent subsequent state changes of the manual approval action or the full pipeline. D. Code Pipeline does not expose a pipeline setting that accepts an arbitrary custom webhook URL as a native notification property. A helpful shortcut is this. EventBridge is the native event source for Code Pipeline state changes. For external HTTPS integrations, EventBridge API destinations can call supported webhook endpoints directly when their authentication and payload requirements fit. Lambda remains useful when custom processing is required. Now for question number 62. This question takes us into compliance automation. Consider this situation. A company uses Amazon EC2 instances running Linux as bastion hosts in a public subnet. Corporate security policy dictates that SSH access, port 22, to these instances must only be permitted from specific known corporate IP addresses. The security team needs an automated alerting mechanism that notifies them immediately if an administrator accidentally modifies any security group to allow unrestricted inbound SSH access 0.0.0.0/0 or :0. How can a DevOps engineer fulfill this requirement using AWS native services? Option A. Enable AWS Security Hub and activate the SIS AWS Foundation's benchmark standard. Configure an Amazon EventBridge rule that matches INOAN_compliant findings for security groups and targets an Amazon SNS topic. Option B. Create an AWS config rule using the restricted SSH managed rule. Create an Amazon EventBridge rule that reacts to AWS config compliance state changes for this specific rule and configure the rule to target an Amazon SNS topic. Option C. Create an Amazon EventBridge rule capturing AWS CloudTrail authorized security group ingress events. Configure the rule to directly target an Amazon SNS topic to alert the security team of the unrestricted rule. Option D. Deploy an Amazon Inspector agent to the bastion hosts. Configure an inspector assessment template to run every 15 minutes, checking for network reachability. Route the findings to an Amazon SNS topic. The answer here is option B. Create an AWS config rule using the restricted SSH managed rule. Create an Amazon EventBridge rule that reacts to AWS config compliance state changes for this specific rule and configure the rule to target an Amazon SNS topic. Here's why. AWS config is the primary AWS service for evaluating the configuration state of your resources against desired guidelines. The managed rule restricted SSH is purpose-built to evaluate whether any security groups in the account allow unrestricted incoming traffic 0.0.0.0/0 on port 22. When a security group is modified to be overly permissive, AWS config detects the change and marks the resource as INOAN_compliant. This compliance state change is immediately emitted to Amazon EventBridge, where a rule can cleanly capture it and route the alert to an Amazon SNS topic for the security team. Now let's rule out the other options. A. AWS Security Hub and the CS benchmarks will detect unrestricted SSH, but Security Hub findings are typically evaluated on a schedule, up to 12 to 24 hours for some config rules backing them. Direct AWS config rules reacting to configuration changes are more immediate. C. Capturing CloudTrail authorized security group ingress events via EventBridge triggers an alert every time any IP is added to a security group. It does not evaluate the CIDR block to determine if it is 0.0.0.0/0 without custom Lambda parsing logic. D. Amazon Inspector evaluates EC2 instances for software vulnerabilities and network reachability, but AWS config is the standard, native tool for evaluating security group rule syntax configurations. Keep this point in mind for the exam. For near real-time alerting on configuration drift, like security groups being open to the world, use AWS config managed rules paired with Amazon Event Bridge and Amazon SNS. Question number 63. Let's go. Scenario. A company operates an Amazon API Gateway REST API that routes requests to a legacy on-premises backend application. Customers report intermittent high latency. Amazon CloudWatch metrics show spikes in API Gateway integration latency, but the DevOps team lacks visibility into the on-premises application's internal execution times. The team needs both application performance logs and distributed trace data from the on-premises application to identify the bottleneck. Telemetry export must not introduce synchronous network calls into the customer request path. Which combination of actions will achieve this goal? Choose 2. Select all answers that apply. Choices. Option A. Install the Amazon CloudWatch agent on the on-premises servers. Configure it to collect the application's performance logs and send them to CloudWatch logs asynchronously. Option B. Enable AWS X-ray active tracing on the API Gateway stage. Instrument the on-premises application so that it calls the X-ray put trace segments API synchronously before returning each customer response. Option C. Enable AWS X-ray active tracing on the API Gateway stage. Instrument the on-premises application with OpenTelemetry to continue the incoming trace context and configure a local CloudWatch agent or OpenTelemetry collector to receive, batch, and export traces asynchronously to AWS X-ray. Option D. Modify the API Gateway integration so that the on-premises application appends internal execution timings to the HTTP response body returned to customers. Option E. Write custom code in the on-premises application to call the CloudWatch put metric data API synchronously before returning every customer response. The answers that work here are Option A. Install the Amazon CloudWatch agent on the on-premises servers. Configure it to collect the application's performance logs and send them to CloudWatch logs asynchronously. And Option C. Enable AWS X-ray active tracing on the API Gateway stage. Instrument the on-premises application with OpenTelemetry to continue the incoming trace context and configure a local CloudWatch agent or OpenTelemetry collector to receive, batch, and export traces asynchronously to AWS X-ray. This is the best choice because it provides the required application performance logs without placing a synchronous AWS API call in the customer request path. C provides current distributed tracing instrumentation and local asynchronous collection. OpenTelemetry instrumentation creates the spans, while the local CloudWatch agent or OpenTelemetry collector batches and forwards trace data to X-ray out of band. B. A synchronous put trace segments call in the request path directly adds network latency and uses an older X-ray specific integration pattern instead of the current OpenTelemetry direction. D. Returning internal timings in the customer response exposes implementation details and adds telemetry handling to the synchronous application response path. E. Calling put metric data synchronously before every response adds avoidable request latency and provides metrics rather than end-to-end distributed traces. For current AWS distributed tracing, prefer OpenTelemetry instrumentation with a local collector or CloudWatch agent that exports traces asynchronously to X-ray. Avoid synchronous telemetry API calls in the request path. Next, question number 64. Next, let's move into infrastructure as code. A DevOps engineer is automating the provisioning of AWS development environments to keep up with rapid engineering growth. The network infrastructure, VPCs, subnets, and route tables, is managed by a separate networking team using a core AWS CloudFormation stack. This core stack exports the necessary VPC and subnet IDs. The DevOps engineer must author a CloudFormation solution for the development environments. Each environment requires multiple complex resources, including application load balancers, auto-scaling groups, and databases. To keep the templates manageable, the engineer wants to separate these resources logically, but deploy them as a single cohesive unit that consistently references the networking team's exported values. The environments must be easily updatable. Which approach meets these requirements most efficiently? Options. Option A. Use CloudFormation nested stacks. In the root template, use the AWS CloudFormation stack resource to define the infrastructure components. Use the FN Import value intrinsic function within the resource properties of the root template to retrieve the networking values, passing them as parameters to the nested stacks. Use CloudFormation change sets on the root stack for updates. Option B. Use a single CloudFormation template. Use the FN import value intrinsic function within the parameters section of the template to dynamically set the default values for the VPC and subnets. Deploy instances of this template using CloudFormation stack sets. Option C. Use CloudFormation nested stacks. Author the nested stack templates to use the FN getAtt intrinsic function to pull the VPC and subnet IDs directly from the networking team's stack name. Update the environments using CloudFormation change sets. Option D. Use CloudFormation stack sets to deploy the application resources. Use the FN import value intrinsic function in the root stack. Configure a macro to dynamically resolve the exported values and inject them into the stack set instances during deployment. In this case, choose option A. Use CloudFormation nested stacks. In the root template, use the AWS CloudFormation stack resource to define the infrastructure components. Use the FN import value intrinsic function within the resource properties of the root template to retrieve the networking values, passing them as parameters to the nested stacks. Use CloudFormation change sets on the root stack for updates. This works because to manage complex, multi-component infrastructure consistently, CloudFormation nested stacks are the AWS best practice. They allow you to define dedicated templates for load balancers, ASGs, and databases, and orchestrate them from a single root stack. Because the networking team exported the VPC and subnet IDs from their stack, the DevOps engineer can use the FN import value intrinsic function in the root stack's resource properties to retrieve them. These values are then cleanly passed down to the child, nested stacks as parameters. Updates are safely managed by generating a change set against the root stack. The remaining options can be eliminated because B. You cannot use FN import value within the parameters section of a CloudFormation template. It is only valid in the resources and output sections. C. FN getAtt cannot retrieve values from completely independent stacks managed by other teams. FN getAtt only retrieves attributes from resources defined within the same template or from a nested stack backup to the root. To cross independent stack boundaries, you must use FN import value cross-stack references. D. Stack sets do not use macros to resolve FN import value dynamically in this manner. Stack sets are designed to deploy identical templates across multiple accounts/regions, not to orchestrate complex single-environment architectures referencing local exports. The main takeaway is CloudFormation cross-stack references, using export and FN import value, allow independent stacks to share values. You cannot use FN import value inside the parameters block. You use it inside the resources block to pass values into nested stacks or instances. Question number 65. Scenario. A company manages a web application hosted on Amazon EC2 instances. The underlying infrastructure is provisioned using AWS CloudFormation. Currently, developers manually build the application, upload artifacts to Amazon S3, manually execute CloudFormation stack updates, and manually SSH into EC2 instances to deploy the new application code. The company wants to fully automate this deployment process using AWS Code Pipeline, AWS Code Build, and AWS Code Deploy. However, a strict governance policy requires a manual approval step to occur after the infrastructure changes have been calculated, but before any AWS resources are modified or the application code is deployed to the instances. Which combination of steps will implement this automated workflow while satisfying the governance requirement? Choose 2. More than one answer may be correct. Options. Option A. Configure an AWS Code Deploy deployment group targeting the EC2 instances. Ensure the AWS Code Deploy agent is installed on the instances. Option B. In AWS Code Pipeline, configure an action to create a CloudFormation change set for the infrastructure updates. Add a manual approval action immediately following it. After approval, configure an action to execute the CloudFormation change set, followed by an AWS Code Deploy action for the application code. Option C. In AWS Code Pipeline, configure an action to execute a CloudFormation stack update. Add a manual approval action immediately following it. After approval, configure an AWS Code Deploy action to deploy the application code to the updated EC2 instances. Option D. Configure AWS code build to generate a cloud formation template. Add a manual approval action in code pipeline. After approval, trigger an AWS Lambda function to deploy the infrastructure and SSH into the EC2 instances to pull the application code. In AWS code pipeline, add a manual approval action. After approval, configure an action to create a cloud formation change set, followed by an action to execute the change set, and finally an action to trigger AWS Elastic Beanstalk for the code deployment. The required selections are option B. In AWS code pipeline, configure an action to create a cloud formation change set for the infrastructure updates. Add a manual approval action immediately following it. After approval, configure an action to execute the cloud formation change set, followed by an AWS code deploy action for the application code, and option A. Configure an AWS code deploy deployment group targeting the EC2 instances. Ensure the AWS code deploy agent is installed on the instances. The company requires automation while maintaining a strict governance gate. Manual approval must happen before resources are modified. In code pipeline, the AWS Cloud Formation Deploy provider allows you to split updates into two distinct actions: create or replace change set, and execute change set. By placing a code pipeline manual approval action between these two, reviewers can inspect the pending infrastructure changes before any actual AWS resources are mutated. B. To deploy the application code to the EC2 instances without manual SSH, AWS code deploy is required. The instances must run the code deploy agent and belong to a defined code deploy deployment group, which the pipeline triggers after the infrastructure changes are executed. A. Here's why the alternatives are not suitable. C. If you execute a cloud formation stack update before the manual approval step, the infrastructure resources are modified immediately without human oversight, violating the core governance requirement. D. Lambda and SSH represent a brittle, custom, and anti-pattern approach to deployment. AWS Code Deploy is the native, robust service for deploying code to EC2 instances. AWS Elastic Beanstalk is a platform as a service, PaaS, that provisions its own EC2 instances and load balancers. The scenario explicitly states the infrastructure is already managed via cloud formation stacks, making code deploy the correct in-place deployment tool. Here's a useful exam tip. To require human review of infrastructure changes before they are applied via AWS code pipeline, use the cloud formation create or replace change set action, followed by a manual approval action, followed by the execute change set action. Next, question number 66. This is a medium-level challenge. A company operates a strict production AWS environment. All applications run on Amazon EC2 instances within auto-scaling groups. The instances stream their secure authentication logs to Amazon CloudWatch logs via the CloudWatch agent. To satisfy a security compliance mandate, any EC2 instance that experiences a manual interactive SSH login must be automatically terminated within 24 hours of the login event. The auto-scaling group will handle provisioning a replacement. How can a DevOps engineer automate the enforcement of this termination policy with the least operational overhead? Option A. Create a CloudWatch logs metric filter matching the SSH login event. Trigger a CloudWatch alarm that sends a message to an Amazon SQS. Use a fleet of worker EC2 instances to read the queue and schedule an event bridge rule to terminate the instance 24 hours later. Option B. Create a CloudWatch logs subscription filter that triggers an AWS Lambda function upon detecting the SSH login event. Have the Lambda function apply a specific tag, for example, to terminate true to the offending EC2 instance. Create an Amazon Event Bridge scheduled rule that runs daily to invoke a second Lambda function that terminates all instances bearing this tag. Option C. Create an Amazon Event Bridge rule listening for SSH login events via AWS CloudTrail. Configure the rule to trigger an AWS Systems Manager automation runbook with a delay step of 24 hours, followed by an AWS change instance state step to terminate the instance. Option D. Create a CloudWatch log subscription filter targeting AWS step functions. Have the state machine execute an immediate Lambda function to terminate the EC2 instance, ensuring the 24-hour compliance window is easily met. The right response is option B. Create a CloudWatch log subscription filter that triggers an AWS Lambda function upon detecting the SSH login event. Have the Lambda function apply a specific tag, for example, to terminate true to the offending EC2 instance. Create an Amazon Event Bridge scheduled rule that runs daily to invoke a second Lambda function that terminates all instances bearing this tag. Let's look at the reasoning. This solution leverages serverless event-driven architecture to meet the requirement with minimal overhead. The EC2 instances are already streaming logs to CloudWatch logs. A subscription filter easily scans the log stream for the exact SSH login pattern in real time. The filter triggers a fast, lightweight Lambda function that tags the specific instance, for example, to terminate true. An Amazon Event Bridge scheduled rule running daily or more frequently if desired, as long as it's within 24 hours, triggers a second Lambda function that scans for the tag and terminates the instances. Because the instances are in an auto-scaling group, they are replaced automatically without affecting availability. The other choices do not work because A. Using an SQSQ and a fleet of worker EC2 instances to schedule terminations adds massive, unnecessary compute costs and operational maintenance compared to serverless Lambda functions. C. CloudTrail captures AWS API calls, control plane. SSH logins, data plane, happen at the OS level and are not logged by AWS CloudTrail. CloudTrail cannot detect SSH logins. D. Using step functions to wait 24 hours for every single SSH login is possible, but can lead to a massive number of long-running state machines, increasing costs and complexity unnecessarily compared to a simple tag-and-sweep scheduled approach. Exam tip. AWS CloudTrail does not log OS-level interactions like SSH sessions or internal database queries. To detect OS-level events, stream logs via the CloudWatch agent and use CloudWatch logs metric filters or subscription filters. Question number 67. Let's go. An e-commerce platform is exclusively hosted in the EU, West, 1 AWS region. The architecture consists of Amazon EC2 instances in an auto-scaling group behind an application load balancer, ALB, with an Amazon DynamoDB table serving as the primary data store. Following an aggressive marketing campaign in North America, users in the United States are reporting unacceptably slow page load times due to geographic network latency. A DevOps engineer has been tasked with expanding the application's footprint into the US, East, 1 region to minimize response times for North American users, while ensuring both regions remain highly available and synchronized. Which combination of actions will achieve these goals? Choose 3. Choose every option that satisfies the requirement. Choices. Option A. Convert the existing Amazon DynamoDB table in EU, West, 1 into a DynamoDB global table, replicating it to US, East, 1. Option B. Provision a new ALB and a new EC2 auto-scaling group in the US, East, 1 region. Configure the new ALB to route traffic to the local auto-scaling group. Option C. Create a new DynamoDB table in US, East, 1. Configure AWS DataSync to continuously replicate the database files from EU, West, 1 to the new table. Option D. Update the existing ALB in EU West, 1 to act as a global load balancer and attach the new US, East, 1 auto-scaling group as a secondary target group. Option E. Configure Amazon Route 53 with latency-based routing records pointing to the ALBs in both EU, West, 1, and US, East, 1. Option F. Configure Amazon Route 53 with a failover routing policy, designating EU, West, 1 as the primary record and US, East, 1 as the secondary record. The correct answers are Option A. Convert the existing Amazon DynamoDB table in EU, West, 1 into a DynamoDB global table, replicating it to US, East, 1. Option B. Provision a new ALB and a new EC2 auto-scaling group in the US, East, 1 region. Configure the new ALB to route traffic to the local auto-scaling group. And Option E. Configure Amazon Route 53 with latency-based routing records pointing to the ALBs in both EU, West, 1, and US, East, 1. The main reason is to deploy an active multi-region architecture for low latency. The data layer must be synchronized globally. Amazon DynamoDB global tables provide fully managed, multi-region, active replication, ensuring data is available locally in both regions. A. The compute layer must be deployed in the new region. A new application load balancer and auto-scaling group must be provisioned in US East 1 to process the local requests. B. The routing layer must direct users to the closest region. Amazon Route 53 latency-based routing evaluates network latency from the user's location and automatically routes their DNS query to the region. ALB that provides the fastest response time. E. Let's quickly check the incorrect choices. C. AWS Data Sync is designed for migrating file and object data, NFS, SMB, S3, into AWS, not for continuous, real-time database replication for DynamoDB. DynamoDB Global Tables handles this natively. D. An application load balancer is a regional resource. It cannot act as a global load balancer, routing traffic across different AWS regions. You must use Route 53 or AWS Global Accelerator for cross-region routing. F. Route 53 failover routing implements an active-passive architecture. 100% of traffic would continue going to EU West 1 until it failed, entirely defeating the purpose of reducing latency for North American users. A helpful shortcut is this. 4 multi-region, low-latency architectures using DynamoDB and EC2/ALB. Use DynamoDB global tables for the data tier, provision ALBs in both regions for the compute tier, and use Route 53 latency-based routing for the DNS tier. Question number 68. This is a harder question, so check every requirement carefully. Scenario. A large enterprise is migrating dozens of legacy applications to AWS. These applications are maintained by different teams using a diverse mix of programming languages, Java, Node.js, Python, Go, and rely on various operating system dependencies. Currently, each team uses a different on-premises release process, leading to high maintenance overhead and frequent deployment failures. The company's leadership mandates a unified, automated delivery pipeline on AWS. The solution must centralize source control, provide a consistent deployment methodology across all teams, and reduce the underlying operating system maintenance tasks to absolute minimums. Which architectural approach will satisfy these requirements most effectively? Choices. Option A. Consolidate all application source code into a single AWS code commit repository using different branches for each team. Use AWS code build to compile the code. Use AWS code deploy to push the applications to a large, centralized fleet of Amazon EC2 instances running a standardized Linux AMI. Option B. Create separate AWS code commit repositories for each application. Use AWS code build to compile the applications and bake them into distinct Amazon machine images, AMIs, for each team. Use AWS CloudFormation stack sets to orchestrate the deployment of EC2 auto-scaling groups using these AMIs. Option C. Create separate AWS code commit repositories for each application. Use AWS code build to containerize each application and push the resulting Docker images to Amazon Elastic Container Registry, Amazon ECR. Use AWS code pipeline and AWS code deploy to deploy the images to Amazon Elastic Container Service, Amazon ECS, using the AWS Fargate launch type. Option D. Create separate AWS code commit repositories for each application. Use AWS code pipeline to orchestrate AWS Elastic Beanstalk deployments for each team. Configure the Elastic Beanstalk environments to use custom Amazon EC2 instances maintained by the central operations team. The answer here is option C. Create separate AWS code commit repositories for each application. Use AWS code build to containerize each application and push the resulting Docker images to Amazon Elastic Container Registry, Amazon ECR. Use AWS code pipeline and AWS code deploy to deploy the images to Amazon Elastic Container Service, Amazon ECS, using the AWS Fargate launch type. Here's why. The primary goals are to centralize source control, provide a consistent deployment method for applications written in completely different languages, Java, Python, Go, Node.js, and minimize underlying OS maintenance. Containerization, Docker, abstracts the diverse programming languages and OS dependencies into a standardized artifact format, an image. By compiling these into Amazon ECR and deploying them to Amazon ECS using AWS Fargate, the company achieves a completely unified pipeline. Crucially, AWS Fargate is serverless compute for containers, meaning the DevOps team has zero underlying EC2 instances or operating systems to patch or maintain, fully satisfying the requirement to reduce maintenance to the absolute minimum. Now let's rule out the other options. A. Consolidating all independent applications into a single repository using branches for different teams is a massive anti-pattern that destroys version control isolation. Furthermore, deploying completely different language stacks to a single shared EC2 server leads to severe dependency conflicts, dependency hell. B. Baking unique AMIs for dozens of different applications requires massive EC2 management, patching, and OS lifecycle overhead, failing the requirement to minimize OS maintenance. D. Elastic Beanstalk automates deployments, but provisioning custom EC2 instances still requires the central operations team to manage, patch, and monitor the underlying operating systems, whereas AWS Fargate completely eliminates this burden. Keep this point in mind for the exam. When managing highly diverse application stacks, different languages, frameworks, and OS dependencies, and needing to eliminate underlying OS maintenance, containerization with Amazon ECS or EKS running on AWS Fargate is the optimal architecture. Question number 69. Let's go. Scenario. A development team uses AWS Code Commit for source control and integrates changes through pull requests. An AWS Code Pipeline builds and tests the application after changes reach the main branch. Broken changes are being merged too often. The DevOps engineer must automatically run unit and integration tests for every pull request revision and prevent that revision from being merged unless the tests pass. Which solution meets these requirements with the least operational overhead? Option A. Create an Amazon event bridge rule for code commit pull request created and pull request source branch updated events that starts an AWS code build project. Associate a code commit approval rule template with the main branch that requires one approval from the code build service roles assumed role ARN. Configure code build to run the tests and call update pull request approval state with approve for the current pull request revision only when the tests succeed. Option B. Create a code commit approval rule template that specifies the AWS code build project ARN itself as the required approver. Attach the template to the repository and rely on code commit to start the project automatically. Option C. Modify the existing AWS code pipeline to trigger on arbitrary pull request source branches and skip deployment when the source branch is not main. Option D. Create an AWS code commit notification rule whose target is the code build project and configure the notification rule to block the merge button until the build finishes. The best choice is option A. Create an Amazon event bridge rule for code commit pull request created and pull request source branch updated events that starts an AWS code build project. Associate a code commit approval rule template with the main branch that requires one approval from the code build service roles assumed role ARN. Configure code build to run the tests and call update pull request approval state with approve for the current pull request revision only when the tests succeed. This is the best choice because Event Bridge starts the tests whenever the pull request is created or its source revision changes. Code commit approval rules can require approval from an assumed IAM role, including a role assumed by code build. Code build approves the current pull request revision only after the tests pass, so the approval rule provides the merge gate that the original build status only design lacked. B. A code build project ARN is not itself an approver identity, and an approval rule does not automatically start a code build project. C. Reworking a deployment pipeline around arbitrary pull request branches adds unnecessary orchestration and does not by itself create a code commit merge gate tied to successful tests. D. Code commit notification rules do not use code build projects as native blocking approval targets and do not synchronously disable merging until a build finishes. Running tests on a pull request and enforcing the test result are separate concerns. Use Event Bridge and code build to run the tests, and a code commit approval rule satisfied by the code build assumed role to gate the merge. Next, question number 70. A DevOps engineer reviews an AWS code build project that compiles a Go application and copies the resulting binary to a central Amazon S3 artifact bucket shared by several internal AWS accounts. The build spec currently uploads the object with this command, AWS S3CP. ACL authenticated read myapp S3 // corporate artifacts bucket A security audit notes that the authenticated read ACL grants read access to the global authenticated users group. The company wants access controlled only through explicit policies for approved internal principles. Which solution resolves the vulnerability most effectively? Options. Option A. Remove the ACL authenticated read option. Configure S3 object ownership as bucket owner enforced so ACLs are disabled, and use the bucket policy to grant S3. Get object only to approved internal account roles. Option B. Keep ACL authenticated read and add a bucket policy allow statement for the approved internal accounts without removing the existing ACL grant. Option C. Change the upload to ACL public read and use IAM permissions boundaries on internal developer roles to restrict who can download the object. Option D. Keep the authenticated read ACL and add additional bucket ACL grants for the approved internal account IDs. Go with option A. Remove the ACL authenticated read option. Configure S3 object ownership as bucket owner enforced so ACLs are disabled, and use the bucket policy to grant S3. Get object only to approved internal account roles. This works because bucket owner enforced disables S3 ACLs and makes policies the access control mechanism. Removing authenticated read eliminates the broad authenticated users grant, and an explicit bucket policy can then grant object access only to approved internal roles. The remaining options can be eliminated because B. Adding an allow for internal accounts does not remove the existing authenticated read ACL grant. C. Public read is even more permissive, and permissions boundaries on internal identities cannot restrict unrelated external principals reading a public object. D. Adding narrower ACL grants does not remove the existing broad authenticated read grant and continues to rely on legacy ACL-based access control. The main takeaway is the S3 authenticated read ACL means the global authenticated users group, not users in your own AWS account. Prefer bucket owner enforced and policy-based cross-account access. Next up is question number 71. Here's what is happening. A development team builds a serverless backend using AWS SAM, AWS Lambda, Python, and Amazon RDS for PostgreSQL. The source code is stored in AWS Code Commit. The Code Commit repository already has an Amazon Code Guru Reviewer Association that was created before November 7, 2025, and remains active. During a security review, auditors discover hard-coded database credentials in Python modules. The company requires automated source code checking during pull requests and a secure replacement for the credentials. Which solution uses the existing controls most securely with the least additional operational overhead? Here are the options. Choice A. Use Amazon Code Guru Profiler on the Lambda functions to identify hard-coded credentials. Store the credentials as standard strings in AWS Systems Manager parameter store. Choice B. Use the repository's existing Code Guru Reviewer Association to analyze pull requests for security issues, such as hard-coded secrets. Store the database credentials in AWS Secrets Manager and update the application to retrieve them dynamically. Choice C. Enable AWS Security Hub to scan the code commit source files for plaintext secrets. Store the credentials in an encrypted Amazon DynamoDB table. Choice D. Configure Amazon Inspector Code Security to create a new code commit repository association and scan the repository. Store the credentials as unencrypted Systems Manager parameters. In this case, choose option B. Use the repository's existing Code Guru Reviewer Association to analyze pull requests for security issues, such as hard-coded secrets. Store the database credentials in AWS Secrets Manager and update the application to retrieve them dynamically. Existing Code Guru Reviewer Repository Associations continue to analyze code commit pull requests even though new associations can no longer be created. AWS Secrets Manager is purpose-built for storing and managing secrets such as database credentials, allowing the Lambda code to retrieve them at runtime instead of embedding them in source. Here's why the alternatives are not suitable. A. Code Guru Profiler analyzes runtime performance rather than performing static pull request review for hard-coded credentials, and standard parameter store strings are not an appropriate secure replacement. C. Security Hub aggregates security findings and posture information. It is not a source code scanner for code commit repositories. DynamoDB is not the purpose-built secret service. D. Amazon Inspector Code Security does not provide a new code commit repository association, and storing credentials as unencrypted parameters would not satisfy the security requirement. Here's a useful exam tip. Code Guru Reviewer is in maintenance mode. Existing repository associations continue to work, but new associations cannot be created. Use Secrets Manager for application secrets, such as database credentials. Here comes question number 72. The difficulty level here is medium. Here's the scenario. A company is refactoring its web application from a monolithic Amazon EC2 architecture to a serverless architecture utilizing Amazon API Gateway and AWS Lambda. Previously, the company used Amazon Route 53 weighted routing to perform canary releases, shifting 10% of traffic to a new auto-scaling group to test features before full cutover. The DevOps team must retain this canary release capability in the new serverless architecture without manually managing DNS weights. Which deployment strategy provides native canary release capabilities for this serverless stack? The choices are: Option A, define the API Gateway and Lambda functions using an AWS Serverless Application Model, AWS SAM, template. Use AWS Code Deploy to manage the deployment, utilizing the Canary 10% 5 minutes deployment preference type to natively shift traffic between Lambda aliases. Option B, deploy the API Gateway and Lambda functions using AWS Elastic Beanstalk. Configure the Elastic Beanstalk environment to perform a rolling update with an additional batch, simulating a canary release. Option C, define the resources using AWS CloudFormation. Implement an AWS step function state machine to update the CloudFormation stack. Wait 5 minutes for manual verification, and then complete the deployment. Option D, deploy the API Gateway and Lambda functions using AWS OpsWorks. Create a custom chef recipe to split incoming API Gateway traffic using custom header inspection. The right response is Option A. Define the API Gateway and Lambda functions using an AWS Serverless Application Model, AWS SAM, template. Use AWS Code Deploy to manage the deployment, utilizing the Canary 10% 5 minutes deployment preference type to natively shift traffic between Lambda aliases. Let's look at the reasoning. AWS Serverless Application Model, AWS SAM, integrates natively with AWS Code Deploy to provide advanced deployment strategies for serverless applications. By specifying a deployment preference in the SAM template, such as Canary 10% 5 minutes, Code Deploy orchestrates the traffic shifting automatically. It provisions the new Lambda version, shifts 10% of the API Gateway traffic to it, waits for 5 minutes, monitors CloudWatch alarms for errors, and if successful, shifts the remaining 90% of traffic. This completely replicates the legacy Route 53 Canary capability with zero custom DNS management. The other choices do not work because B, AWS Elastic Beanstalk is a PaaS designed for provisioning and managing traditional EC2, Docker, or Tomcat environments. It is not used for deploying or orchestrating Amazon API Gateway and AWS Lambda serverless stacks. C, AWS step functions can orchestrate complex workflows, but writing a custom state machine to manually manipulate CloudFormation stacks and traffic weights introduces significant operational overhead compared to the native AWS SAM/Code Deploy integration. D, AWS OpsWorks is a configuration management service that uses Chef or Puppet to configure Amazon EC2 instances or on-premises servers. It is not used to deploy or manage serverless architectures. Exam tip. To implement canary or linear deployments for AWS Lambda functions easily, use AWS SAM and specify a deployment preference. For example, Canary 10% 5 minutes. AWS Code Deploy handles the alias traffic shifting and automatic rollback natively. Question number 73. An enterprise uses AWS IAM Identity Center for all human access to AWS accounts. A strict security policy therefore prohibits local IAM users and member accounts. If a developer creates a local IAM user, the company requires a near real-time automated response that removes the prohibited user and notifies the security team. Which combination of steps will meet these requirements? Choose 3. More than one answer may be correct. Review the options. Choice A. Create an Amazon Event Bridge rule that filters for the Create User API call delivered through AWS CloudTrail. Choice B. Create an Amazon Event Bridge rule that filters only for the getLogin profile API call. Choice C. Configure the Event Bridge rule to invoke an AWS Lambda function that removes any login profile, access keys, and attached or inline policies for the new IAM user if present, and then deletes the IAM user. Choice D. Configure the Event Bridge rule to invoke a Lambda function that attaches a permissions boundary to the IAM Identity Center role used by the developer, but leaves the newly created IAM user in place. Choice E. Configure the Event Bridge rule to target an Amazon SNS topic whose subscriptions notify the security team. Choice F. Configure a scheduled Lambda function to pull CloudTrail log files every 5 minutes for create user events and send email through Amazon SES. The required selections are Option A. Create an Amazon Event Bridge rule that filters for the Create User API call delivered through AWS CloudTrail. Option C. Configure the Event Bridge rule to invoke an AWS Lambda function that removes any login profile, access keys, and attached or inline policies for the new IAM user if present, and then deletes the IAM user. And Option E. Configure the Event Bridge rule to target an Amazon SNS topic whose subscriptions notify the security team. The main reason is it detects the prohibited create user operation in near real time. C restores the required state by removing any dependent credentials or policies if present and deleting the local IAM user itself. E provides immediate human notification through SNS. Event Bridge can fan out the same event to remediation and notification targets. Let's quickly check the incorrect choices. B. GetLogin profile is a read operation and does not reliably detect creation of every IAM user. D. Restricting the creator role does not remove the prohibited IAM user that already exists. F. 5-minute polling is slower and adds custom polling logic when Event Bridge can react directly to the API event. A helpful shortcut is this. When policy requires that a resource must not exist, remediation should restore that desired state. Disabling one possible credential is not equivalent to deleting a prohibited IAM user. Question number 74. Let's go. We're moving on to CI/CD pipelines. Scenario. A DevOps engineer is designing a unified CI/CD pipeline for a sprawling microservices application. The application source code is hosted in a private GitHub repository. The pipeline must orchestrate deployments across 3 different compute platforms: Amazon Elastic Container Service, Amazon ECS, Amazon EC2, and AWS Lambda. The release process requires a manual approval action before the deployment reaches production. Which AWS service configuration will meet these requirements most natively? Options. Option A. Create an AWS code pipeline. Use the GitHub connection for the source stage. Add a manual approval action. Use AWS Code Deploy as the action provider in the deploy stages, as it natively supports ECS, EC2, and Lambda targets. Option B. Create an AWS code pipeline. Use the GitHub connection for the source stage. Add a manual approval action. Use AWS Elastic Beanstalk as the action provider in the deploy stage to distribute the application to ECS, EC2, and Lambda simultaneously. Option C. Configure GitHub Actions to perform the build and add a manual approval step in the GitHub workflow. Use the AWS CLI within the GitHub action to trigger AWS CloudFormation templates that provision the ECS, EC2, and Lambda resources. Option D. Create an AWS code pipeline. Configure AWS Code Build as the single deploy provider and write bash scripts in the build spec.yml to deploy the application manually to ECS, EC2, and Lambda via the AWS CLI. Go with Option A. Create an AWS code pipeline. Use the GitHub connection for the source stage. Add a manual approval action. Use AWS Code Deploy as the action provider in the deploy stages, as it natively supports ECS, EC2, and Lambda targets. Here's why. AWS Code Pipeline is a fully managed continuous delivery service that supports manual approval actions natively. It integrates smoothly with GitHub via AWS CodeStar connections. For the deployment phase, AWS Code Pipeline utilizes specific action providers. AWS Code Deploy is the native action provider designed explicitly to orchestrate deployments across Amazon EC2, AWS Lambda, and Amazon ECS. By configuring code deploy deployment groups for each respective compute platform, the DevOps engineer can manage all three within the same code pipeline natively. Now let's rule out the other options. B. AWS Elastic Beanstalk is a PaaS for EC2 and Docker instances. It does not natively orchestrate or manage deployments to AWS Lambda or standalone Amazon ECS clusters. C. While GitHub Actions is a valid CI/CD tool, using it to trigger CloudFormation templates via the CLI for complex ECS/Lambda rollouts requires significant custom scripting and lacks the native visual approval gates and managed traffic shifting that Code Deploy provides. D. AWS Code Build is a continuous integration tool used for compiling source code and running tests. While it can run bash scripts via the AWS CLI, using it as a deployment engine bypasses the rich deployment strategies, health tracking, and automatic rollbacks provided natively by Code Deploy. Keep this point in mind for the exam. AWS Code Deploy is the primary deployment engine used in AWS Code Pipeline when targeting Amazon EC2, AWS Lambda, or Amazon ECS. You have completed Set 4 of the DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please like this video, subscribe to Tech with Kaushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.